So what exactly are standing waves? We can visualize this as a guitar string with both sides on fixed points called nodes, since they're not moving. A wave can be propagated down and reflected back on itself, causing antinodes and nodes where they're not moving. This is visualized with a frequency generator and a base plate of metal. That base plate is connected to a electromagnetic oscillator, which is connected to the frequency generator. Sand is then put onto the base plate, and the frequency generator is turned on at a specific frequency to cause standing waves. This will cause a physical representation of the nodes and antinodes, where the sand particles are pushed away and held in. The antinodes will push those sand particles away, since it is constantly moving, and the nodes, where there's no motion, will collect all the sand particles.
So on to the problem. A guitar string is 91 centimeters long and has a mass of 4.3 grams. From the bridge to the support post, the length is 56 centimeters and the string is under a tension of 517 newtons. What are the frequencies of the fundamental and first two overtones? So what exactly is a fundamental frequency? We know a standing wave is a frequency held between two nodes that oscillates back and forth. So the fundamental frequency is essentially the largest portion of that wave that can fit between these two nodes. The second harmonic is the second largest portion that can fit between these two nodes and is represented as such. Is known as our first overtone. Now this is also known as the second harmonic, as the fundamental frequency is known as our first harmonic. If we keep going on in a manner as such, we can see that the first, second, and third harmonics are essentially adding portions of the wave to it between these two nodes, and the first, second, and third harmonics will look as such. Now we can look at these full wavelengths as a crest and a trough, where the correlation between the wavelength and the number of harmonics is 2 times the length of the string divided by the number that corresponds to the harmonics.
We're able to find a correlation between our wavelength and frequency. As the wavelength goes down, our frequency will go up. This is represented as a formula of N is describing the harmonic and F1 is our fundamental frequency. So to find our first overtone, it's just 2 times the fundamental frequency, and to find the third, 3 times the fundamental frequency.
So first, let's list all of our formulas and variables that we're going to be using. We know that V, or velocity, is equal to lambda times the frequency. We can also rewrite this as frequency equals the velocity divided by lambda. We know that our lambda is 2L, where L is the length between the two nodes. Our velocity is equal to the square root of the tangent force divided by mu. We combine all these to get the fundamental frequency formula. Our fundamental frequency formula is going to be the square root of the tension force divided by mu divided by 2L. Mu can also be written as mass divided by length of the string. So the length of our string is 91 centimeters or 0.91 meters. The mass is 4.3 grams or 0.0043 kilograms. The length between the two nodes is 56 centimeters or 0.56 meters. Our tension force is 517 newtons. So we can substitute all these values into our fundamental frequency formula to get that the fundamental frequency is 295 hertz. Now we can multiply this by 2 to meet the first overtone or the second harmonic to be 590 hertz. We can then take this and multiply the fundamental frequency by 3 to get our third harmonic or our second overtone at 886 hertz.
So in summary, our fundamental frequency is approximately 295 hertz. Our first overtone is approximately 591 hertz. And our second overtone is approximately 886 hertz. Thanks for watching.